Welcome. This is part 2 of solving linear systems of equations. So remember what we're doing is illustrating the equation operations. There are 3 of them: swap locations, multiply one equation by a non-zero quantity, and then another operation that involves operation number 2, but further involves adding the new equation obtained after multiplying by non-zero quantity to another equation, and then doing some substitution, replacing one of the equations. So we're going to apply these type of operations to the following example, and we're going to use some notation here. So suppose we're interested on this system, maybe as a matter of illustration, based on the type of notation that we just previously discussed. If we wanted to represent this and this type of notation, this is going to be called the matrix vector representation of the system. In this case, there are 3 variables. So there is x1, there is x2, and there is x3. On the right side of the equal sign, there are 3 numbers, and they are 4, 5, and 6. And then the coefficients that are multiplying each of the variables. On the first equation, we have coefficients 1, 2, and 2. On the second equation, we have coefficients 1, 3, and 3. And on the last equation, we have coefficients 2, 6, and 5. So this would be the matrix vector representation of these equations, okay? But what we're going to do next is to apply equation operations. So the first thing we're going to do is that we're multiplying equation number 1 times this alpha equals negative. This means that we're going to multiply by non-zero quantity called alpha, which is -1. It's another way of saying take the first equation, multiply every term in the first equation by -1, and then add that to the second equation. So by doing so, if we multiply the first equation, every term in the first equation by -1, we would have minus x1 minus x2 minus 2x3, and that equals -4. So we're doing that multiplication across the board. We're multiplying every single term on the first equation by -1, and what we want to do next is to now take that new equation and add that to the second equation, okay? And so we add every term 1x1 plus minus x1, then that would give, adding up, right, that would give us 1x1 plus minus 1x1, that gives us 0x1. 3x2 minus 2x2 gives us 1x2, and 3x3 minus 2x3 gives us 1x3. And then on the other side of the equal sign, we have 5 added to -4, and that would be 1. So this here is a new equation, and the instructions here says replace equation 2. So what we're going to do is to substitute equation 2 with this new equation obtained in this form, and that's precisely what we have here, okay? And so now we have a new a different system than the original system, and because all we did was to apply these equation operations, this new system is going to be equivalent to the original one. Okay, so what we do next is that we multiply equation 1 by -2, add that to equation 3, and replace equation 3. Okay, so multiplying the first equation by -2 is going to give us the following, right? Remember, we have a 1 here, so multiplying equation 1 by -2 gives us -2x1 minus 4x2 minus 4x3, and then on the other side of the equal sign, we're multiplying 4 by -2, that would be -8. And so the instruction says that we want to add that to the equation 3, we want to add that to equation 3, but this is referring to the previous equation 3, okay? And instead of going, I could go back one page. So this is referring to this equation 3. So I'm going to write that equation 3 above our calculated here equation, new equation after that operation. And so the former equation 3 is 2x1 plus 6x2 plus 5x3 equal 6. So now what comes next is that we want to add these two equations, right? So we have 2x1 plus negative 2x1, that gives us 0x1, 6x2 here, 6x2 plus negative 4x2, and that gives us 2x2, and then 5x3 plus negative 4x3 is what gives 1x3, and 6 plus negative 8 is given minus 2. So by doing so, we obtain a new system of equations, and what we have managed is that in this system, only the first equation has a coefficient of 1 multiplying x1, but equation 2 and equation 3 are such that now that variable x1 has disappeared. Okay, so that is convenient. Originating zeros as coefficients of the variables is convenient when trying to find a solution for the system. So let's see what we do next. What we do next is now we're going to work with the second equation, and we're going to multiply equation 2 by the non-zero number alpha, and alpha is minus 2. In other words, multiply equation 2 by negative 2 and add that to equation 3. So this is referring to go to this system here, multiply equation 2 by negative 2. That's going to give us, you can ignore the 0. Well, if you want, you can have the 0 there. So that would be 0, 0x1 minus 2x2 minus 2x3, and that equals, we're multiplying everything by minus 2, so this is minus 2 on the other side of the equal sign. So now what we do is we add that to equation 3 and replace equation 3. 0 plus 0 is 0. Minus 2 plus 2 is 0. That's where this 0 comes from. And then minus 2x3 plus 1x3 is given minus 1x3, and then we have minus 2 plus minus 2, that gives us this minus 4. So the important thing is that by doing so, now we have managed to have a 0 coefficient on the last equation. Okay, so let's see what happens next. What happens next is that we take that equation 3 in the previous calculation, multiply equation 3 by negative 1, and this is what the system looks like. So this system, it actually can be written as in this form. We can ignore the coefficients with 0. So the elegance of this system that has this shape now, by having some 0 coefficients, what happens now is that there is a shape that resembles a triangle. Okay, so in fact, if we were going to write the matrix form for this, so the matrix vector form for this newer system is going to be the following. So on the right side of the equations, the B1, B2, B3 are 4, 1, 4. We have 3 variables, right? So that's what we have in this vector here. So x1, x2, and x3. And then this is the matrix of coefficients. That rectangle in this case is a square, but so this has coefficients 1, 2, 2, and then 0, 1, 1, and then 0, 0, 1. So the matrix of coefficients in this case, by virtue of these zeros, okay, these zeros were labor intensive to obtain. These zeros, they result from applying equation operations to the system. But the elegance, well, the convenience is that now this matrix, if I enclose the numbers that are non-zero in this matrix, those numbers are enclosed by a triangle. Okay, and so this matrix that has zeros in certain positions here is going to be called a triangular matrix. So there's something elegant about linear systems that can be transformed into triangular systems, triangular because of this shape of the numbers, and it's because once in this form we say, hey, look, the last variable has to be 4 according to what we read from this expression. So x3 is 4. If x3 is 4, I can go back to the second equation and substitute. So the second equation will read x2 plus 4 equals 1, and that tells me right away that here x2 would be minus 4 plus 1, which is minus 3. So now we have a value for x3, a value for x2, and then both of these values, this value and that value, can, and will be used in equation 1. So we can substitute x2 and we can substitute x3 and then find a value for x1. So in this case is left to you as an exercise to do the last part of that calculation I was just explaining. So you're going to go and substitute with the value of x3, find a value for x2, and with the values of x2 and x3, go to equation number 1, substitute those values, solve for x1, and you will end up with a value for x1, a value for x2, and a value for x3, and those values will determine the values that belong to the set of solutions, the so-called solution set. So verify that those values are the solution of the transform system. The transform system is going to be referred as the reduced system, and also verify that those values satisfy the equations of the original system. Thank you.